I guess before we jump in, we should maybe say who we are. My name is Caleb Schoepp. I'm a software engineer at Fermyon. I've been there for about a year, work on the Fermyon cloud and some of the upstream open source stuff like Spin, which we'll be playing around with today, and SpinCube too.
I'm Justin Pflueger. I also work at Fermyon. I'm a solutions engineer, so I engineer solutions. And yeah, work with Fermyon customers to kind of build out applications and kind of take advantage of WebAssembly on the server.
Awesome. So I want to start by talking about what you guys are going to be walking away with today. And really kind of the meat of it is some hands-on experience with WebAssembly. So we're going to be getting our hands dirty there and actually playing around with WebAssembly on the server side. And specifically, we'll be using the open source tool Spin, which you'll learn more about in a second. And we'll be learning things about like how to route requests into your Spin application, kind of all the features you can use in a Spin app like KV stores or generative AI models, those large language models. And then we're also going to be like running these locally and deploying to Fermyon Cloud and kind of experiencing that full gamut there. Just kind of a quick agenda for today. We're going to spend the first kind of like 15 to 20 minutes just talking about a few things here. We'll do kind of a 101 level introduction to WebAssembly and kind of a 101 level introduction to Spin. Give everybody here some context on that. Then we'll do a brief overview of what the workshop's going to look like. And then the majority of the time is just going to be kind of a live coded walkthrough of the workshop, and we'll go through a step.
Quick show of hands. Who's heard of or used WebAssembly before? Got a couple. Anybody Fermyon fans, Spin fans out there? All right, well, we'll make some new ones. Hey,
awesome.
We got
one in the
back
back
there.
Okay,
Sweet.
Cool. New crowd to evangelize to. Awesome. So we'll jump right in here. Now, I just want to give an opportunity here at the start. We've got 3 ways we can kind of work through this workshop. The first way is you can install the dependencies locally and do it that way. Second way is you can go to our workshop, our github.com Fermyon workshops, download that and use a dev container. Or kind of the way we recommend that people work through this is using a VS Code code space. So if you go to this URL using the QR code there, you can click on code, clone, and then go to the code spaces tab and generate a code space. It's a full editor online. It will have all the dependencies for you to kind of work on out of the box. So I'll give maybe a couple more seconds in case anybody wants to scan that and get that going, but we'll walk through that later.
And if anybody gets stuck or has questions, just raise your hand. I'll come around and help you. There was a little mix-up with the venue today. There were supposed to be tables and stuff for you to get out your laptops and set them out, but yeah, we just have chairs today, so.
We'll make do, we'll make do. Okay, I don't see any more scanning of the QR code there, so we already did this poll. Awesome. Okay, so starting with kind of like a 101 on WebAssembly. What are the 3 most important things we should like know about WebAssembly? Well, first of all, WebAssembly is a specification. And more specifically, WebAssembly is a specification of a binary instruction format. So really what you should think of WebAssembly as is it's a compile target. You can take your source code in Rust or TypeScript or Go or whatever language that supports WebAssembly and compile that into this WebAssembly instruction format and then execute that later. And also, we should know that WASM is an abbreviation of WebAssembly. You're going to hear me say WASM and WebAssembly interchangeably. You're going to see it interchangeably on the slides and everywhere, so that's a good thing to keep in mind. Here's kind of just like a visual of what this means, right? You've got your code. You, for example, maybe use your Rust compiler to compile it to a WebAssembly module, and then that module can be executed by a WebAssembly runtime, which could be running in a container, it could be running locally, it could be running in the cloud on an IoT device. Now, whenever I talk publicly about WebAssembly, I always like to kind of come back to 4 reasons why you should care about WebAssembly. Because it's like, sure, it's this cool new tech and there's a bunch of hype about it, but like, why does it matter? And I think there's 4 reasons. First reason is security. And so WebAssembly offers us a sandboxed execution environment. And in addition to that, it also offers us something called capabilities-based security. So what do I mean by sandboxed execution environment? What I mean by that is that when a runtime is executing WebAssembly, it's called a guest module, it's sandboxed, it's secure, and there's guarantees in the WebAssembly runtime that the code's never going to be able to break out of that sandbox. It's not going to be able to do a buffer overflow or any sort of attack like that and attack the underlying device that's executing that WebAssembly. We're also going to hear a bit more later about capabilities-based security, which is basically saying you have to explicitly require access to things on the system, and then you can audit those capabilities you're requesting. The second reason I think we should care about WebAssembly is performance. And really, performance is just kind of table stakes, I think. We're not going to see adoption of WebAssembly without performance. Third, WebAssembly is polyglot. And what does that mean? Poly, many, glot languages means that WebAssembly supports a wide array of languages. So you can take a Python program or a Rust program or any number of languages and all compile them to WebAssembly and have them cooperate together nicely. And then fourth, WebAssembly offers like a great portability story. Similar to Java, where you compile it to that bytecode, and then anywhere you have a runtime for that Java bytecode, you can run it. That sort of write once, run anywhere story. Similar thing in WebAssembly. You have a runtime for all the different systems and architectures you want to run on, and you get great portability out of that WebAssembly code. When we talk about WebAssembly, you're also going to hear something called WASI come up a lot. And WASI stands for WebAssembly System Interface. And to understand what WASI is and why it matters, I think it's important to think about the history of WebAssembly. And so WebAssembly originated as a technology for the browser to bring non-JavaScript code into the browser. But that meant it was really tied to JavaScript and web APIs, things like the DOM and such. And so as there's kind of this movement to bring WebAssembly to the server side, there arose this need to have access to things on your system, like the file system or environment variables or other things like that. And so WASI is really a specification around how do we standardize these imports into a WebAssembly module so that it can access these things on the system and behave more like a POSIX program. And really, WASI is continuing that story of portability, standardizing what it means to interact with a file system, whether you're on a POSIX system or a Windows system or whatever, and also that security through capabilities-based security. You have to explicitly request access to the file system, and then you can audit whether you want the code to have access to that. Again, coming back to this polyglot story, WebAssembly has great support across a wide array of languages. On our developer site, we have a table tracking that, and this is really just growing. It's amazing how fast support is landing for WebAssembly across languages. Now, we talked a bit about performance. Originally, WebAssembly was meant to be executed in these JavaScript runtime engines, V8, SpiderMonkey, those kind of things. And that's, of course, because WebAssembly originated in browser. That was the kind of original context. But again, as this kind of like push to the server side for WebAssembly, we found a need for new runtimes. And so that's kind of where we get these WASI runtimes, such as WASM-Time or WASM-3, things like that. And these are really kind of meant to be used in more like functions as a service use cases or like IoT and things like that. Not for this talk, but I think it's really cool to point out there's like some crazy engineering here to get this kind of like near native execution speed. So it's a really cool space. So, we've talked about those 4 things that make WebAssembly great. What are some good use cases for WebAssembly, obviously outside of the browser? 3 kind of come to mind. First is cloud and functions as a service. So why is that a good fit for WebAssembly? Well, you think about what you're doing in functions as a service. You're executing arbitrary code from some customer. So you want it to be secure. You want it to be sandboxed so you can safely execute their code. You want it to be performant, so you need near native execution speed. And you need it to have really low cold start times and be cheap to ship around, so you want small binary sizes, which WebAssembly gives you. So that's a great fit for WebAssembly. And we'll be getting a lot more into that, because that's really kind of what Spin offers, is that sort of functions as a service paradigm. The second one here is plugins. Again, coming back to the security, being able to trust arbitrary code in those small sizes makes it a great fit for plugin architectures. I forget the exact quote, but our CEO always likes to quote basically that WebAssembly is the last plugin architecture you'll ever need, because we'll support all the languages, right, that kind of polyglot nature, and be able to compile anything down to WebAssembly for a plugin. And then third, IoT is, of course, like a great use case. We don't really focus on it much at Fermyon, but again, the security, the performance, the small binary sizes, all are great reasons to use WebAssembly in the IoT space. Sweet. So that's kind of like the whirlwind tour of WebAssembly. That should be like a 4-hour talk, but we compressed it into 5. Now we're going to talk about Spin. And so what is Spin? Well, WebAssembly is great. We talked about all these things, reasons we like it. but it's like super new, and the developer experience is like really rough around the edge. And so Spin is really the developer tool for kind of building these serverless WASM applications super easy. So we started this about 2 years, is that right, Justin, at Fermyon? 2 years ago?
Yeah, 2 years and change.
2 years and change. And so here's kind of like an overview of what using Spin looks like. And there's kind of really 3 marquee commands in Spin. So the first one is spin new. And spin new is basically how you go from like a blinking cursor to having an application in front of you. And so, today we will be going through in TypeScript, and you want to build your TypeScript serverless WebAssembly application. You'd go spin new, and that will scaffold out a TypeScript application for you that you can then write your code into. And it will also build a manifest, which we'll be looking at later, which kind of describes how do I compile my application to WebAssembly, what capabilities do I want to have access to, all those kinds of things. Once you've hit spin new and you've spent some time developing your code, then you need to compile it down to WebAssembly, and that's where spin build comes in. And spin build, the command, basically just abstracts away all the complexity of compiling your code down to WebAssembly. Then once you've spin built, you have your compiled WebAssembly application, then you can run spin up for a local testing experience, which will serve your application. You can test it locally. You could deploy it to Fermyon Cloud, which we'll talk about in a second. You could deploy it to a Kubernetes cluster. You could really anywhere you can run Spin, you could run that Spin application. Spin has many features. We'll be seeing a lot of them today. It has support for serverless AI, which is going to play largely into our demo today. Support for things like key value stores and databases, relational databases, config, and we even support multiple types of triggers. So you can trigger your Spin application like a web server with an HTTP trigger. So you hit a route and your application is triggered, or you can set it up for triggers like Redis. So a message is published to a channel on Redis, and you trigger your application to process some of that data, or MQTT. I mean, the possibility for triggers is really kind of endless in Spin. Just as a brief aside, I kind of want to point out on the developer.fermyon.com site, we have a Spin Up Hub, which after this, if you want to check out more about Spin and kind of like see examples of things people have built, that's a great place to go. Okay, so I alluded to this earlier. Fermyon Cloud is basically our opinionated hosting solution for Spin apps. So if you want to run your Spin app in production, you can, of course, just spin up a VM or a container and run Spin up, or use our new project we just released, SpinCube. But Fermyon Cloud, we view as kind of the easiest way to get going. It's literally just spin cloud deploy, and you've got your WebAssembly application running in the cloud. And it also offers some really cool opportunities with serverless AI that I want to talk about. So we'll get into this more once we start working through the workshop here real soon. But we're going to have an application, and it's going to be accessing a Llama 2 chat, generative AI model. And that's pretty straightforward. That's great. Makes it easy to hook your function up to that and use that. But let's think about what that means when you deploy this WebAssembly function to the cloud and you want to run that. And you could also kind of compare this to using AI in Lambda. It's great. You've got a request coming into your Lambda or your Spin function, but that starts up really quick because all the benefits of WebAssembly. But what if you have to spin up a GPU every single time you want to access that generative AI model? That's obviously not going to be very fast. And so within Fermyon Cloud, we've built this system where we're able to multiplex all the GPU usage from all these different Spin apps in the cloud to our own pool of GPUs in the back end. And so what that gives us is really kind of 2 key things. One, it gives you really low cold start times, because no longer is a request coming into your app and then you need to spin up a GPU and wait for that. You just have an already warmed up GPU in the back end running. But 2, it also keeps your costs down, because the only GPU time you're really paying for is the actual inferencing of that. So here's kind of an example of what an application doing that might look like, and this is kind of similar to the application we'll have by the end of the day, where that blue line, you have a inference request coming into your Spin application, and it's using these large language models, which are like pooled in the background for really low cold start times. And then you can use key value stores to cache the responses, or put context embeddings into a SQLite database and do all those kinds of things. I'll just breeze by this for now. I think that will all kind of add up a bit more at the end once we've done it.
Fun fact here, Fermyon Cloud is So our GPU pool is built on Civo and Green Cloud. So every time you inference today, you'll be warming a pool somewhere in London.
Yep.
Fun fact.
I like that one. Okay, so it's time for the workshop. Let's get hands-on. Enough talking. Today we're going to be doing a Magic 8-Ball workshop. And I don't know if any of you ever played with Magic 8-Balls growing up. I certainly did not. I had to Google what they are. But for the uninitiated, a Magic 8-Ball is a ball that you come to and you can shake it, and then it will come up with an answer to your question. So you might come up to the Magic 8-Ball and say, am I going to have a good day today? And you would shake the Magic 8-Ball, and it would magically come up with an answer and say, the answer is unclear. Not very helpful, but maybe fun. Fun fact, I learned this while I was Wikipediaing Magic 8-Balls. It's actually just a D20 that's floating in some fluid, and when you shake it, it just floats up to the top. So cool, pretty cool technology. Okay, so we're going to be building a spin app that's replicating this kind of Magic 8-Ball experience, and we're going to be not only generating these answers, but we're going to be generating them with AI, so that's how we're using the generative model. And then we're also going to be using the key value store to cache those responses. Here's kind of the steps of the workshop. So we're going to start with setup, which is kind of just installing Spin or setting up your code space to get going there. And then we're going to do getting started, kind of play around with the hello world experience. Then we'll roll that into something a bit more useful, build a JSON API that will respond with that Magic 8 response, just kind of with random answers. We'll augment that then and use the LLM model to actually generate those answers. And then we'll put a pretty front end on it, so we have kind of a nice user experience around that. And then we'll cache those values with the key value store. I think that'll probably take most of our time, but depending on how things go, we have a bit of an extra exercise.
Yeah, the extra exercise is going to be kind of a choose-your-own adventure. We haven't finished all the code for it, so yeah.
Okay, so here's a QR code, and that should take you to the workshops. So yeah, like we said earlier, unfortunately, there was a bit of a mix-up, and we weren't set up with tables today. But I encourage you to pull out the laptop on your lap and kind of work through it here. I'll switch my screen in a second here once people have a chance to go for the QR code. There's 3 ways we're kind of supporting this workshop again, which is locally, basically installing the dependencies directly on your machine. You can clone the workshops directory and use the dev container through like VS Code. Or my personal recommendation is just go to GitHub and set up a code space where it'll spin up that dev container remote for you, and then all the dependencies will just work and you can do it out of your browser.
And if you get stuck at any time, just raise your hand and I'll come around and help.
Oh, password for Wi-Fi? Penguins, yes. Fast or slow, I'm not sure which network to choose. I was thinking it was maybe the game. Okay. One's 5 gigahertz, I've learned, and one's 2.5. Okay, so seems like everybody's got that QR code scanned. I will head over to the workshop. Okay, and we'll just give a bit of time at the start here because the installation process might be a little bit slow on the Wi-Fi, perhaps. Seems like my Wi-Fi is a little bit slow. Very slow. Well, I might have to change to do it locally if it doesn't load. So I guess I'll just do that to show people for a second. Come on. Okay, so we're going to start with setup. And there's really, as I said, 3 paths. The code spaces should be pretty straightforward. Just raise your hand if you can't figure out how to start that. And then maybe the least straightforward one is just configuring your local environment. So for anybody using Linux, WSL2 on Windows or Mac OS, you can go ahead and install Spin by using our brew tap. And then we can go ahead and install some templates. Those aren't directly necessary for this tutorial, but they'll be handy for later. And we'll just give a couple more minutes here. Oh, yeah. Whoa. Font size. Why terminal? Does that work? There we go. Can people see that fine in the back? Yes, go ahead. So if you click like clone, the green one, and then there should be a code spaces tab. And it will take a second to generate the code space because it builds a container, but. Justin, just fine. Oh, okay, perfect. Let's do. Awesome. So by a show of hands, can I see who's still working on getting a code space running or installing things? Okay, still going. I know.
While other folks are getting set up, did we have any questions about WebAssembly, Spin, or anything from the first portion of the talk? Cool. Perfect comprehension. Great job.
Yes. Go ahead.
The question was, what languages does Spin support? So it's a good question. So we have kind of tiers of languages that Spin supports right now. Tier 1 languages is what we call like languages that have support for generated bindings for our SDK. So going back to what Caleb was talking about before, the WASI spec is built on top of this additional spec called WIT, which is WebAssembly interface types. And that's how we describe external kind of interactions from WebAssembly. So that's kind of how we express the Spin SDK. And there's five-ish languages. Depends if you include TypeScript as an additional language on top of JavaScript. But 4 or 5 languages right now that we would call Tier 1 support. And then probably 10-ish languages that we would call Tier 2 that compile to WebAssembly, but you don't have access to the Spin SDK because they're still building out support in WIT to kind of generate those bindings for the SDK. But you can still use those languages kind of like a CGI script, essentially. So standard in would be your request, your like kind of raw HTTP request, and then standard out would be your response. Yeah.
Just for people who walked in, we're just starting to set up and install Spin. There's 3 ways we can do it. There's a code spaces on the workshops where you can spin that up online. People might be having trouble with that. I can't get my code space to load, so I'm not quite sure how the internet's working for other people. And so maybe locally might be a better solution too. And we have steps in the workshop setup page for doing it locally. Just need to install spin from our brew tap. Awesome, and I'll just do another show of hands. Who's still working on setting up the spin environment? Couple people, okay. We'll give it like a few more minutes and then we'll just jump in here and do the demo and we'll just make sure you guys are tracking through. We don't have sample apps for Python prepared. You can take a crack at it. It should, all the SDKs are there and work. But we'll be going through TypeScript here, and any sample apps are all in TypeScript or Rust. Okay, I think we probably have close enough, and if people fall behind, just raise your hand and we'll make sure to come around and get you caught up and get spin running. But I want to dive in and start talking about this here. Okay, so we're all set up. Let's go to getting started. Awesome. So, you know, we can all start by running spin version, make sure we've got spin running on our machine. And as I said, there's kind of this flow of spin new, spin build, and then spin up. So we're just going to see what that looks like, just kind of locally here. So I'm going to be doing TypeScript up here at the front. So I want to build a new application, and I'm just going to do this in this directory here. So I'll do spin new, and then I'm going to pass the application of the name. I'm going to say hello TypeScript as the name of my application. And then I'm going to use a template called HTTP TypeScript. So this is going to start kind of a scaffolding command. It's going to ask for a description of my application. So I'll give it a description, and I'll say something along the lines of hello world app. And then it's going to ask for a path. And so by default, this will make more sense later when we see the manifest, but by default, we're going to be using an HTTP trigger, which means it's HTTP requests coming in that are going to trigger your component. And so path is saying, what path should I allow to come into the component? What mapping of paths? And so we're just going to stick with the default here, which is just saying any path can come into this component, and we'll support that. Awesome. So I should see a hello TypeScript folder now, and I can navigate into that. Yes. Is that big enough for everybody in the back? I see some leaning forward, so I take that as a no. How's that? I see a thumbs up. Cool. Awesome. Okay, so we're in the directory here, and we'll just do a tree to see what we've got scaffolded out for us. We got a README, And then we've got kind of all the accoutrements you would expect of a typical TypeScript project. So you've got your package.json for your dependencies, and you've got your source directory with an index.TypeScript file and all that kind of stuff. So let's maybe start by looking at the TypeScript file here and see what that looks like. OK. So it's really simple. We're just exporting a handle request function. And that handle request function takes in a request and returns a async response. And we're not doing anything fancy in here. We're just returning a 200 status code, text plain content type, and hello from TS SDK as the type. Now we've got the package.json, just like you would expect with a JavaScript project here. And you can see that we're importing the Fermyon Spin SDK. And this is what allows us to use these kind of custom HTTP request and response types. Now, kind of where the real meat on the bone comes from is the manifest I keep talking about. And that's the spin.toml. So here we've got a spin.toml. So this is configuring a number of things about your Spin application. In that application section, it's just kind of metadata, who's the author, what's the description of this app, what version, all that kind of stuff, the name of your app. But the really important part is the trigger.http section and then that component section. So the trigger part is saying, I have an HTTP trigger, and I want to take anything coming in on the route /.. which is meaning any possible route, and I want to map that to my hello TypeScript component, which I have defined below. So then I have my hello TypeScript component, and this is what's taking that source code we have in that source.ts file and saying, OK, you need to run this command to build this JavaScript into WebAssembly, and then this is the underlying WebAssembly that should be used to run that component. Now, there's a bunch of magic in the package.json build scripts that actually does the work of compiling to WebAssembly, but that's the beauty of Spin, that it's scaffolded for you, and then you just don't have to worry about all that compilation process. Great, so we've got the application here. Is there anything else I want to show you? No, so that's it. So now we want to build this application, so we can go spin build. And this is actually going to fail because I forgot the first step in a, here, I'll just kill it. In a TypeScript application, we first need to install the dependencies. So I'll npm install those dependencies. If I had thought about it, I probably would have done that earlier, pending on conference Wi-Fi. We'll see how that goes. And so this is going to install the dependencies for the app. And then we'll be able to run spin build, which will compile it to WebAssembly. Any questions on that so far? Wow, that's some slow internet. I think I chose fast. Slow was pretty fast. OK, I'll have to try that one out. OK, we're switching to the backup plan because that's being slow. And I'm going to use Rust, because that does not need to install a bunch of dependencies slowly. So I'll just do these steps quick. Hello Rust, template, HTTP Rust. We'll skip the description for now. And this is going to have all the same things. The spin.toml is going to look slightly different with a different build command, but same kind of underlying thing. So we'll run spin build, and that's going to build our app here. That needs to update create indexes too. Awesome. So now we've built the Spin app. And for Rust, that's going to live under target WASM32. Might be release, actually. Nope. So you can see we've got that hello rust.wasm file there. Now, if we go spin up, It's going to take our built application. It knows from the manifest where to look for that WebAssembly file. Let me just make this a bit bigger. And we can see that we've now got our app running. And so if I just go ahead and copy paste this, and then in a new terminal, if I curl that endpoint, we see hello Fermion responding back to us. Awesome. Now, just as kind of a demonstration, we can hop in here and edit the source and say, hello WebAssembly, and rebuild that application because we need to recompile that WebAssembly to use that new hello WebAssembly string. Run spin up again, and recurl that endpoint. We should see hello WebAssembly. Awesome. Socket timeout on the npmi. Okay, well maybe we'll see how doing TypeScript up here at the front is. Awesome, so that's getting started. That's what scaffolding an app in Spin looks like. How are we doing? Any questions? Anybody stuck, not making it through that part? Go ahead.
So this is kind of off a little bit of the topic, but if you've got an application that's written, say, in Python and Java, do we compile each one of those and then combine them together into what I would consider the final build?
Yes, yeah,
Okay.
absolutely.
And then if you've got, unfortunately, low-level C functions that are talking to an IoT, how do you have to obviously build a WebAssembly API for that? Is that kind of how you do the IoT deployment stuff when you're trying to look at board-specific systems?
Yeah, go ahead, Justin.
Yeah, so you would need to kind of use WIT and the WASI spec to kind of poke a hole from the WebAssembly guest into the host to be able to access that hardware device.
Okay.
And that can kind of be your own kind of interface, whatever you want to create that. And then you can use like Zig compiles to WebAssembly.
Okay.
So.
I just kind of wanted to know the basics. I don't want to like freak out.
Yeah, no worries.
Yeah.
That's part of the component model. That's something that just got WASI 02 just got finalized. Let's see, January, I think.
That sounds right, yeah.
Yeah.
And I mean, to put it another way, Spin does as much as possible to hide WebAssembly in a lot of ways. Like, you should not even really have to think about it. But all the configurations and options are there to do all the plumbing you want and run your C with your special APIs and all that stuff under the hood.
I do some work in an oil refinery, and they have lots of sensors that don't support, it's all serial connection. So we have a big-ass MUX that we talk to that abstracts it. So it's kind of painful, and I'm just trying to figure out how I can make it easier.
Right.
Totally.
And another way you could do it is, since Spin is like all open source, you can create your custom triggers. So we have a lot of like community contributed triggers. So say you wanted to run some piece of WebAssembly based off of some hardware event, you can write your own thing in like C or Rust.
Just get the hardware to send a signal event into the system. Okay.
Yep.
Thank you.
Yeah.
Awesome. So for anybody who just came in, we're just going through the workshop flow here. It's just at github.com, Fermion Workshops. You can set it up locally or in a code space and just raise your hand if you need to get caught up. Great, so we've demonstrated that kind of getting started flow. Let's move on to the next step here and build ourselves a JSON API. So what we want to do is we just want to build something really simple that takes in a question and returns just a random answer from these 4 examples, and then we'll spice that up later. So again, we'll kind of use the process of spin new, scaffolding out an application, and then we're going to build it with some of this fancier code. So let's just get going on that. So first I'll kill this hello world TypeScript I had, then I want to do spin new magic 8 ball TS. and we're just going to use the HTTP TypeScript template again, a magic 8-ball application. And this time, we're going to use a specific path, and we're going to say, only take in requests to the magic 8 path. Oh, yes, thank you. /magic 8. Awesome. So now we've got our magic 8-ball application here. Similar thing. This time I'm going to learn my lesson in npm install while I'm coding, so it's hopefully done. Awesome. So we've got a similar handle request function this time, except instead of just like directly returning a response, we actually want to use a question that's coming in from the request. And so how we're going to do that, or sorry, I'm getting ahead of myself. We're not even going to use the question yet. We're just directly returning a random answer. And so, pretty straightforward stuff here, just a normal JavaScript function that is taking in an answer, and I can dump that directly into my application. Oops. And then we can also see we are, whoops. Sorry, folks. We're directly using that response instead of returning this 200. Awesome. We're getting a red error here because we haven't npm installed yet. That's okay, that'll go away. And we will wait again. Looks like it's making progress though. And thankfully, this will be the last time we'll have to npm install for this app. Awesome. Okay, now I can spin build the app. That's compiling the WebAssembly using Webpack to do all the bindings and such. And then I can run spin up. Awesome, we've got it going. If I curl it, we get no response as expected because we're not hitting the magic 8 endpoint. So it's not routing through to our component. But if we add the appropriate magic 8, we'll see some JSON response. Pipe that through to JQ. Awesome. And we'll see that it's randomly returning a response. So, this is obviously like really, really simplistic, but it kind of gives you an idea of how you might structure sort of a simple backend API out of a spin application and have different routes running to different components for your different services or whatever. You can obviously crank the complexity up from there. Anything else we want to hit here, Justin? I don't think so. Any questions? Yes?
So I'm having some code spaces issues where I can build and spin up the application, but I can't see the endpoints.
Yeah, so we're hearing a question about some code space issues. We'll help out with that. It's likely, so Codespaces does this kind of fancy port forwarding stuff, which can sometimes cause issues. So we'll help out there. Awesome. Okay, so we got a JSON API. Now it's time to kind of make this a little bit more fancy and use the AI. Go ahead. That's a great question. Let's go see. So I need to see where the WASM file is living, and the WASM file is living under target. Target. Get some human sizes. So 2 megs. And go ahead. Yeah. Yeah. Yeah, and you're saying specifically using different languages within Spin. Sure. The short answer is no. They're typically going to be similar, but the way that different languages support WebAssembly is going to result in pretty different WebAssembly binaries. So just as a brief example, Python, the way we support that dynamic language is we actually bundle in the Python interpreter compiled to WebAssembly, which is going to increase the size. That's a whole other conversation of in the future we'll be able to link that out and things like that, but it will be different. I saw a question there.
No, I was going to ask a question about if that binary is compiled
Correct.
That probably what adds up to the two, almost 2.5 minutes, right?
Correct. Yeah, just to repeat the question, he's saying that all the dependencies you've compiled into that is going to add to the size of that.
Yeah, and actually your node modules won't be included in the WASM file. What takes up a decent chunk of this is the JavaScript interpreter. So,
So it's the interpreter.
yeah. Yeah, so our current, the JavaScript SDK you use today is actually built on top of our Rust SDK, and it uses a project called Javi, which I think is built on top of the Quick.js interpreter. So we take all of that, compile it into Rust, and then we use that, our Rust SDK to actually invoke the interpreter and load up your JavaScript. But then Webpack should strip out most of the node modules that aren't used. Yeah.
Like due to the tree shaking and everything.
Yeah.
Totally.
So if you're looking for a small deployment, what language should you be using as the original?
Smallest, probably, smallest with the best support would be Rust. There's also quite a few like community contributed things around Zig and C++ as well. That should all work.
Awesome. Okay, so now we're going to really kind of dive into the meat of this and start using the generative AI model, specifically Llama 2 chat model, to generate these responses. So the way we make this easy is we have an SDK written around this that you can use in your Rust or JavaScript application to access that LLM model. And so what we're going to do here is we need to modify our request handler to take in the question like I was talking about earlier from the request. So we want to take in that request body, decode it, use that value as our data. Then we want to pass that data into a prompt that will pass off to the chat model, and then that will generate the answer to our question. I'll hand it off to Justin for a second to kind of talk about the prompt, the Llama 2 chat prompt, and how that all works.
Yeah, so as you can see, there's some like specific formatting in here. If you've never used Llama before, these are just instructions that Llama understands to kind of differentiate between what like you want the text generation to use as context. So that's this kind of sys with the brackets around it or the arrows around it. So this portion of the prompt will be interpreted by Llama as contextual information for how to answer the question. And then everything after sys up until the end of this instruction will be interpreted as this is the question or thing that I need to actually generate text for.
Any questions about that before I throw that into the application there? Okay. Okay, so let's start by pulling this question out of the response body here. We will pull up our source code. So we want to pull the question out here, and we need to get some decoders. Let's go like this. So these are just kind of helpers, basically, to do the bytes to string mapping that we need to do in JavaScript. This isn't a requirement in other things like Rust SDKs. Great, so we've got this encoder and decoder now, and we're going to decode the question out of there, return an error if no question was asked. Now we need to change our answer function to not just be randomly returning something, so let's just remove that for now. But instead, we want to do this more exciting thing and use the LLM here. Great. Okay, so we're going to see some errors. That's expected. That's because we're not importing these types from the SDK. No need to import anything extra from the package JSON. It's all coming out of the Spin SDK package. And we'll fix the one last error, and we'll pass in the question that we've parsed out of the body into the answer generator here. Great, that looks like it's going to compile. I'll come over here. We'll run spin build again.
Did you want to show them spin watch since
Yeah.
you built it?
Funny, yeah. So it would be amazing to think about how many times I forget to run spin build. And so I got tired of that, and I built a spin watch command. And spin watch is just basically going to watch for any changes to your source code, just kind of like any other npm watch command, and automatically run build for you, and then directly run up. Great, so we've already got up running. Now, we're going to run this, and there's going to be an error, and let's see why that is. Well, the first obvious error that I forgot about is we didn't pass any data to it, so that's doing its job, so let's pass a question to it. Is this demo going to work? Will be my question. Okay, we got the error like expected. Now remember back in my presentation when I talked about the security of WebAssembly and the capabilities-based security? This is where this comes in. So in order to be able to use this AI model that we want to use, we need to explicitly request the capability to access that model. So we can see this error here. The component does not have access to the Llama 2 chat model. So let's give it access to that. And the way you do that is by adding that to the manifest. So we go back to our application, and we go to our spin.toml, our application manifest. Here in the component section, we need to say, hey, this specific component has access to a model called Llama 2 chat. So we should have seen this rebuild there. And then we can rerun it. And we're going to see another error. Perfect. Oh, the error is because I didn't run it. There we go. OK, another error is expected. So now it's failing because for local development, we expect that it has a Llama 2 chat model locally in your .spin/AI models directory. Now, I have it downloaded locally, and so I'll be able to show that to you. Unfortunately, it's pretty massive. It's like 8 gigs or something like that. And so it's kind of untenable for us to all download an 8 gig model on conference Wi-Fi here. But I can demonstrate this, and then I'll be able to show you in a second how you guys will be able to run it the 2 different ways. So if I just make a directory .spin here, and file exists. Oh, OK. And then if I just link, I have it just stored in one location on my laptop, so I don't have to copy the model around everywhere. And I link an AI models directory here. Perfect. Then I should just be able to run spin up again, because it will be looking at runtime. OK, it's running. Now, the one other reason we might not want to use models here locally is because I'm grinding away this giant Llama 2 chat model on my MacBook. And so this is going to take about a minute to run, which is obviously not great for demo purposes. But it kind of paints to this story of being able to at least use it locally, and you can do workarounds like running smaller models with smaller parameter sizes.
Yeah, by default, it'll use a quantized model to execute on CPU locally. If you wanted to take advantage of GPU execution while running locally, you would have to clone spin and then do a cargo build with the feature enabled. But it is possible. It's just not enabled by default because it massively increases the size of spin CLI.
So while that's chugging away, oh, yes, question.
Just a boring question. I could get the decoder. Something's missing in the code.
Justin will come take a look. Yeah. Thanks for asking. We totally want to help make sure people are sticking along with us. So while this is chugging along, I'm going to show an easier way we can run these models and something a bit more practical for you guys. So we're going to just go into this other directory, and I'll go into our magic 8-ball. And we're going to deploy it to the cloud. And so that's free to do. And it's going to give us access to that Fermion serverless AI function. So the command to do that is spin cloud deploy. So it's going to, once you've built your application, bundle all that up and shoot that off to the API, the cloud. For you guys to do that, Justin, there's a question over there. For you guys to do that, you'll just have to log into Fermyon Cloud. It's really easy, just uses a GitHub account to log in, and then there's like a little auth loop where you do spin cloud deploy, and it'll ask you to go enter a code into Fermyon Cloud. Okay, so we've got it uploaded now. We're waiting for the application to become ready on cloud. That'll take a couple seconds. Awesome, so we've got it running in cloud, and we'll curl it with the data. Is my cloud demo going to work? Maybe, maybe not. All right, to be determined if this is internet issues or app issues. Wouldn't be a live demo without this, though. Awesome, so this is just the cloud dashboard, and we can use this kind of for debugging here. We'll go into our application, and eventually, perfect. So we can see that that worked, and we got our response back. Not sure why that was so slow. I'm guessing just the conference internet here. And we can see we've got some requests that were made into the app, and eventually some of the logs will propagate through onto here. Although, actually they won't, because we haven't added any logging to our application. So that's how we can deploy the application to cloud, and it will run that. And again, you know, I talked about in the slides, but I want to talk about it a little bit more here, of like what's actually happening when this spin application is running in the cloud and it's making a request to GPU to do an inference. What's happening locally is our SDKs directly look for that Llama 2 chat model, you know, in your .spin/AI models folder and directly execute that. But what's happening in the cloud is it's basically taking this request to do some inference, putting it on a queue, along with like multiplexing that in with all the other applications running in the cloud. And then we have our pool of GPUs that are serving this queue of inferencing requests. And so that's how you're able to have all these warmed up hot GPUs serving your inference requests, but not need to pay for that cold start time of starting up the GPUs and only being paying for that when you're using it. Okay, so that's one way you can do it. Another way you can do it is we have this thing called Spin Cloud GPU, which is a little plugin we built that basically eases local development, so you don't have to run that AI model locally. You can sort of proxy it to a GPU that we're running in our cloud. And so you're still spin up locally, running it locally on your machine, but instead of the SDK saying, hey, I'm going to look for this model locally, it's going to proxy through an application you've put in the cloud and make a request to that. So you're going to say spin cloud init, it's going to create this application in the Fermyon cloud, and then any inference you do locally is going to go through that kind of proxy application. So this is another way you can do it, and I'll just quickly demonstrate this. I've already installed the plugin, but you would just need to run this spin plugins install command. Then you need to go to your application here. I'll turn it off. Oh, and just while we're here, I just want to point out that the localhost request we did much earlier, where I said it's going to take forever, did eventually finish, and this is the answer we got from running it locally. This is the answer we got from running in the cloud, and then I'll show the third option here. So we'll kill the spin up, then we're going to do spin cloud GPU, which is just triggering our plugin. If you just do spin, it will show you all the commands, and you can see cloud GPU is a plugin we have. Spin cloud GPU init. That's going to go through the process of initializing this sort of proxy application in the cloud. Failed to deploy. That's interesting. I wonder what's going on there. Oops. Perhaps I corrupted my spin cloud GPU plugin. we'll give it the old college debugging try. If you meant to load from registry, spin cloud GPU help. Interesting. Yes. Question for the group or just need some help? Awesome. Any questions for the group while I try and debug this Spin Cloud GPU plugin? So let's uninstall it and reinstall it and see if that fixes it. Uninstall Cloud GPU. Awesome. Now let's reinstall it. Awesome. There we go. Well, looks like I will have to open an issue in that open source project to see what's going wrong there. Go look at my applications and we should expect to see, come on. Gateway. Looks like I'm having some internet issues here. Anybody have any questions about deploying to the cloud and getting that to work? Do we have anybody yet who's successfully run an inference on the cloud? Not yet. I see people hard and trying. Great question. To really briefly describe why we think WebAssembly makes sense for this kind of functions as a service context, security, you get a sandboxed execution environment, so you don't need to worry about the code people are running, or at least worry as much. Performance, you get like near native execution speed with WebAssembly, while still getting this kind of like polyglot experience where you support all sorts of different languages, and then kind of a portability story, where that's much easier with WebAssembly. A lot more depth to it than that, but that's, I'd say, the TLDR pitch. Okay, well, I'm going to call it here because I'm thinking I'm having internet issues deploying this, and maybe we'll try that in a bit here. I'll move on to the KV thing here and raise your hand if you're getting stuck on the GPU stuff, and Justin will come around and help and make sure you're following along. Great, so we've got the ability to take in a question, generate a response using LLM inference, and that's super easy, but that inference is still expensive. No matter what way you cut it, you're still using a GPU. So it'd be nice if we could cache the responses and every time somebody asks, is my demo going to work? We don't have to say, maybe the internet's not so good. We can cache that response. So how do we do that? You have something to add? No. How do we do that? KV has, Spin has a KV function that allows you to write and read from this sort of key value store that's baked into Spin. So the first thing we need to do that is, again, this kind of capabilities-based security. We need to go into the definition of our component in that manifest and say, yes, I give access to a key value store, a default one. So we'll go here. We'll give access to that. Perfect. Just giving access to a default store. Then we want to kind of add this wrapping layer around our answer function, which instead of just directly calling that LLM, it's going to use our Spin SDK to open up a KV store and then grab based off the key, which is the question, and see, well, let me show a TypeScript example. We're going to see, does this question exist in the key value store already? Yes, it does. Okay, great. Go get that value and decode it, and then respond with that instead, with the small caveat that if the response was ask again later, well, we want to try it again to recalculate that answer. Otherwise, okay, we haven't found this key in the key value store. Let's go ahead and generate that answer, store it, and return it. So we can add this to our app. Get or set answer. Again, we don't have KV imported. We'll import that here. Update the import. Now let's use it. Let's get or set answer. Awesome. And that should work. So if I spin build here, great, successfully built. Again, could test locally, but we'll get the really slow calculation, inference process. So we're going to try and deploy internet pending. Then if that doesn't work, we can try running it locally here. Spin cloud deploy, if your app already exists, is basically just like redeploying and like updating the version of the application. We'll cheat and do both at the same time. We're going to run spin up here. Locally, the key value store is just backed by SQLite on your machine. That's what it actually is under the hood. And we'll curl to the local host. Is this demo going to work? And let's slap a time on there. Whoops. So that we can compare a cached answer versus not. Bad gateway. You want to try deploying on yours? I'm curious if I just don't have internet or if cloud is broken.
Did you finish your init code?
No, so that wasn't working because of the internet. So we're just still using the local one that I have in the .spin AI models. Yeah. Awesome. Signs point to yes, but no guarantees. Promising. Okay, and we can see that took 40 seconds there. Switch slow. Okay. I am just going to switch internet networks. Maybe I can just hop on Sheena's hotspot real quick. Penguins. Okay. Now we're going to, this is again running it locally with the model again. And we see that it took 2/100ths of a second because instead of running this really slow 40-second inference on our machine, we're just pulling that answer out of the key value store really quick. Let's just try one more time on the slow network. Looks like that deployed successfully. We'll wait for that to be ready here. When this waiting for application to become ready is running, what that actually means is, so we've taken your WASM binary and we've uploaded it into our air quotes cloud, and we're then distributing it across our cluster, so it's on multiple different machines. And so then when a request comes in, it can be routed to any number of machines, and we can spin up your app. And so it's this kind of unique property of WebAssembly as a function as a service that it's not like a Lambda. You don't need to keep a container hot and running to get these low cold start times. You literally just have some WebAssembly on disk, and when a request comes in, you can execute that WebAssembly, and there's still no cold start time, which is one of the cool advantages of WebAssembly. Great. So, oh, I wish I did a time for that. Let's do a slightly different answer so we can compare. Strictly different. So, okay, there we go. About a second, and then if I run it again, we see about a fifth of the time with the caching. Great, so that's in the cloud. Now that my internet's working again, I just want to see if I can demo this cloud GPU. We'll deploy that application. And while that's hopefully deploying, I can just point out the kind of next step in this is, we already understand how to deploy, so we'll skip over that. External DB. So, we're using this kind of built-in key value store baked into the Spin SDK, but we also have support for a number of other external data stores, so like Redis or like SQLite or things like that. So 7 is kind of like an exercise we're leaving to all of you if you want to explore, where, okay, what if instead of using the Spin KV store, I wanted to go to Redis Cloud and spin up a Redis database there and then use that? What would that look like?
Yeah, the nice thing about being able to switch out the KV store on the back end is you don't actually need to do any code changes to be able to do that. You can use the runtime config to just tell the Spin host, hey, I want to use Redis instead of the local SQLite database, which makes it really nice to use when you need to kind of deploy things to different environments. So say you want to develop locally in SQLite, when you go to deploy it to like a Kubernetes cluster or something like that, you want to point it at a Redis key value store. You can also write your own host implementation. I think we have additional ones for, what's the Azure one?
Oh, Cosmos DB?
Yeah, Cosmos DB. So yeah, you can kind of swap out the implementation without any code changes.
Totally. So for anybody curious or wants to pursue that, we have all these sample apps here, and under 7 there's some example source code both in TypeScript of Rust of how you might do that. Great. Back to this cloud GPU. Sorry for all the bouncing around with the internet. This is the option that you're running it locally, but you're using this proxy application in the cloud to access these Fermyon Cloud GPU resources. So it's asking us to set up some runtime config. So we'll just do runtime config.toml, paste that in there. And so this is the runtime config that Justin was talking about, where you can switch up the backends. And one of the configurations you can set in this runtime config is, hey, what do I want to use for my underlying LLM compute? And here we're saying we want to use this remote compute. Here's the URL for this Spin app that's in the cloud, and we'll kind of proxy those GPU requests for you. And then an auth token that was automatically generated. So now if I go spin up, and I go runtime config file runtime config.toml, unable to listen. I have it running somewhere else. We're running locally, but now instead of pointing at that model under .spin AI models, we're pointing at this kind of proxy app, which I will just show quickly here. Fermyon Cloud GPU. That's the app that was generated by Spin Cloud GPU init. We'll make a request to it. So this is locally. Let's just do a new question. How cool is Spin Cloud GPU? And we can see, like 1.2 seconds. So similar times to directly using it in Fermyon Cloud. And again, we would expect the caching. It's like 1/10 the time there. Great, so we got that working. Let's, what's the next step here? So that's the meat of the KV stuff there. I'll stop here for a second. Does anybody have any questions about what we've done so far?
Hi, sir. I came in a little late. What if we integrate the LLM into this Spin application?
Yeah, great question. Yeah, so that was step 3, where we take this, kind of simple JSON API, and then we're now stripping the question out of the request body, and then passing that question off to this function where we generate a prompt for the LLM, hand that to the LLM with the SDK, and generate the response.
We're using the long shot for the LLM.
Correct. And then just the one other notable thing there of making sure you're defining the capabilities the component needs. Sweet. I'm realizing I skipped the front end step. I knew I was missing something, so let's go back and do that. So a little out of order, that's totally fine though. Let's go add a front end on this. So what we're going to learn kind of with adding this front end is that, you know, alluding to an earlier question, can I have multiple components in an application of different languages and such? Yes, absolutely. So we're going to show how that's done. And so what we're going to be using for the front end is just a static file server component. So it's this pre-built component that we've already compiled to WebAssembly, and it basically knows how to take in requests to what other path it's serving under, and then handle those requests and map those to the files that you have in some sort of like local assets directory. So if I go ahead and use the spin add command, which is basically similar to like spin new, except it's taking an existing application and adding a component to that. So I go into my app here and I say spin add something called file server. That's the name of the component using the static file server template. We want it to map to any path. So by default, it looks for any requests coming into static, but in our case, we want to do it under any path. And what, you know, directory of assets do we want it to serve up from? We'll use the default of assets. And then, go ahead, Justin.
Yeah, just a note here. Could you open up the spin.toml file?
Yeah.
So now we've got two paths in here, and one is kind of like a wildcard path. So the way that spin interprets that is it will look for the longest match for your URL. So say you gave it /magic8, it'll route to that WASM file first because that's the longest route with the most like URL components in it. And then anything else that it can find for, it'll default to wildcards. So that's kind of how that works without returning 404s for other paths.
Yeah, and that's a great point to bring up the spin.toml here. Right, so Justin talked about how there's this new trigger route added to the configuration that's pointing with that wildcard to the file server component. And then you're going to notice this file server component looks different than this magic 8-ball component. The kind of biggest difference is with the magic 8-ball component, we're compiling and building it locally. So the source, we're pointing at some local directory, and then we have a build directive, which is saying, hey, when you run spin build, run this command to compile and produce that WebAssembly at that source location. In the case of the file server, we've already built this WebAssembly component for you and are storing it in GitHub. And so you can just point the source directly to the URL, this kind of like pre-compiled release asset. And then, of course, this is another capabilities-based security option where we're saying, hey, I want to give this component explicit access to files with this kind of mapping from source to destination. So that's the spin.toml. If we go and spin up here and we use the runtime config again, so it's quick, fail to load component, invalid mount source assets. Okay, so it's failing, and that's because I have not yet copied over the assets. So if I just go to the sample app here, copy the assets directory, and then go to my app, whoops, and paste in an assets directory, we should see assets. Great, and we've got it running now. So let's curl it again. Hitting the local point, let's use a new question. How is the weather today? Great, pretty quick, still working there. Now let's see what this front end looks like. So if I navigate to the browser, just on the bare path, it's going to serve up this index.html, which we've got in the assets, and I'll show in a second. And we can ask a question today. Is my lunch going to be tasty? Let's see what it says. different question. I've been having trouble with quote escaping in the answers by the LLM, so that might be a little debugging adventure we can go on together. Did it work? Yes, I did. Okay, well, we'll go on a little debugging adventure. Yeah, maybe. So let's start by adding some logging to our app. So this just kind of works like you would expect it to work in a normal application. Let's just see, you know.
Yeah, one thing to note here, something that is being actively worked on in the WebAssembly space is obviously debuggers. You're able to generate debugging symbols, but currently unable to set breakpoints and stuff like that. So something that we're actively working on. Yeah, back to print lines for debugging kind of takes me back.
Yeah. I just actually saw for WASM-Time, which is the underlying runtime, WebAssembly runtime that Spin uses, that they're making movements in the debugging space, which is really exciting.
Yeah.
And, you know, this is pointing to the future, but WebAssembly gives you so many cool opportunities to innovate in this space. Because you have this WebAssembly module that has these like really clearly defined imports and exports, it makes it really easy to implement things like time travel debugging, because you can, at the interface of this module, what's the word I'm looking for? Know anything that's non-deterministic and be able to track that and kind of be able to do this time travel debugging through there. All right, so we've got some logging now. We're using our runtime config. This is on the local host. How's it going? Okay, well, we're getting our answer. Oh, we're turning some kind of weird bracket on the end. Well, let's see how this works in the cloud. And while we're doing that, I'm going to just show you the assets of what we're actually serving. And so the kind of meat of it is just this HTML file, and we've just got this infer function that whenever you hit enter or hit infer, it's basically pulling that question out of the input box there, making a post request to our magic 8 endpoint, and then waiting for that response, and then inserting that reply. Great, so we've got it deployed. Let's go to the cloud version. How is the weather?
Developer error.
Yeah. Source of the error is between the keyboard and developer network.
I think it's probably in your code.
Yeah, I'm not sure what's up with that. Okay, but so besides the JavaScript not working there in the front end, I think we've demonstrated, you know, kind of the key point of this, which is you're able to compose multiple different components. They can be pre-built, or you can be building them locally to kind of compose this experience together. That's the meat of what we want to present. Now, Justin has kind of a further steps of using SQLite and embedding that. Maybe he can step up here and.
Yeah. Before we go on to that, does anybody having issues getting things running either locally or cloud?
Probably an obvious question, but do you guys have this whole tutorial up on the web?
Yeah. Do we have the tutorial on the web? Yeah. So github.com/fermion/workshops. That's where you can find all of this. All this information, all the markdown files, code space, and then if you scroll up, This apps directory here is where all of the answers will be. So yeah, there should be answers in there for all of the sections except for the experiment that we're about to go on. Cool.
Do you want to use mine or do you want to plug yours in?
I'll use mine.
Okay.
I think I have some stuff already.
Yeah, looks good. People can see that in the back, or do we need to zoom in a bit? Back. No complaints? Okay, cool.
Okay, so this is kind of like a bonus exercise. We weren't sure exactly how much time we would kind of take up with the first portion, and it looks like we still have an hour and a half. So, yeah, another portion of the Spin SDK.
Yeah, maybe it got shut off.
Mic was off. Yeah, another portion of the Spin SDK. There's another function called generate embeddings. So let's talk about embeddings for a minute. So far we've done some basic kind of text generation, right? Where we've given Llama 2 a prompt to say, here's our question. Contextually, this is what the function that we want you to serve, and here's our question. And that's cool. And one of the kind of trade-offs that we have to make to be able to kind of run all of these inferencing requests across a bunch of different tenants is in order to have that kind of low latency inferencing requests for everybody, we have to use the same model. So there's no like custom models built into Fermyon Cloud. It's all built on top of just the open source like Llama 2 model. And if you wanted to, run custom models, that's something that we're working with a couple of customers on. So yeah, feel free to find my contact information if you wanted to run custom models. But yeah, that's kind of one of the trade-offs that we have to make. So one of the avenues we can take to kind of give Llama 2 more information is we can insert more context into the prompt that we give Llama 2. So how do we kind of do that? We could just dump a bunch of text in there, but then it has to kind of go through and figure out, okay, what piece is relevant. So another thing that we can do is generate an embedding based on a piece of text. So I think the kind of overarching term for this is called retrieval augmented generation, RAG for short. And this is kind of what OpenAI does when you go to chat with ChatGPT. Nowadays you can ask it about current events or websites, and what it does when you ask about that is it will in its database, it will generate an embedding based on your question and find other pieces of text that are relevant to your question and include it in its prompt. So the way that this works is that for a given piece of text, you can generate a vector for that piece of text. And it's a 384 dimension vector, so essentially just an array of floats with 384 floats in it. So for like one example, if we were to ask the magic 8-ball, will it rain today? It's going to be a random answer because it has no idea what the forecast is. However, if we were able to kind of give it today's forecast, you know, in like some sort of cron job, just go grab the forecast for the day, generate an embedding for that piece of text. So we can start to give the Llama 2 prompt more information by using embeddings. So the way that we're going to try to do this, and I've built this demo before, but I don't have the code 100% ready right now, so it's going to be a little bit of an adventure, is we'll go through like a list of facts. And then we will generate an embedding vector for each of these facts. And then when we go to post our question to the magic 8-ball, we'll generate another embedding vector, and we'll do a vector similarity search and find the closest vector that is to your question, and then grab that kind of fact and include it into the Llama 2 prompt. It's kind of like a dense piece of information. So do we have any questions so far? Yeah. I'm sorry? Yeah, the embedding vector that we use, so we use the all mini LM L6 v2 embeddings model, and that generates a vector of 384 dimensions, or just an array of size 384, so 384 elements, and they're all like float 32s. Yeah. Yeah, are those predefined dimensions? To be honest, I'm not entirely sure. I just know at a high level that if I give it this piece of text, it generates a vector, and I can use that to compare similarity to other pieces of text, kind of doing like a search.
This also is in my area of expertise, but I'm pretty sure the embedding dimensions is just baked into the model. So different models might have just different predefined embedding sizes. Yeah.
Cool. All right, well, let's jump into some code.
So are you actually fetching the current weather in real time to determine what response is going to happen?
No, you wouldn't be doing that in real time. So you you need to kind of precede like all of these vectors that you want to possibly include in your search. So what we're going to take a look at here is using kind of our built-in SQLite database, which is backed by Terso, and that has the SQLite VSS extension, vector similarity search extension, kind of built in. So we'll store these vectors in a SQLite database, and then we'll use a SQLite query to run a vector similarity search, and it'll kind of rank our most similar vectors.
Just to add some color to that we're talking about what we are building right now in this little demo. You totally could. Hypothetically, you could have a spin application where you have your SQLite database and you have a cron trigger that's triggering an application every hour to go fetch current information, generate embeddings for that, load that into the database, have this separate, endpoint that's serving up these inferences. So not what we're doing right now, but totally is something you could do.
Yeah.
So if we have the code already, maybe a good place to start would be showing them the prompt of how we're going to embed that additional context.
Yeah. So I'm just starting from, I'm kind of working off the answer, so building on what Caleb's done so far. Yeah, so this is kind of our basic answer. Inside of this sys section here.
Maybe just zoom in a bit.
Oh, yep. We're just going to add in a spot for, well, you know, first we need to go through in the process of setting up our kind of SQLite database. So the way that I'm going to do this is using it on Spin Cloud. So I think it's Spin Cloud SQLite. So I've already created a SQLite database. And I can see it here. Yeah, so this will be the database that I want to use here is Magic 8. So the way that you would do this if you're trying to follow along, emphasis on trying. Is you would run this spin cloud SQLite create and give it some name. Yeah. And then we're just going to create kind of a basic table for this. So I think I've already got well, we'll just write it out to a file.
And just while Justin's doing that, I want to remind if anybody's stuck on anything or feel free to raise your hand and I'm happy to come around and help.
Cool. So this is just kind of the basic table that I'm going to create here. And I can do this by running spin cloud SQLite execute. Just make sure I get it right. Yeah. So give it the database name. I just called it Magic 8. And then it wants a statement. So you can either kind of copy paste the kind of text in here, or you can use the @ symbol to tell it what file to use. And that completed successfully. Cool. So kind of like Caleb did earlier, where we gave our Spin app access to Longitude Chat, we're going to give it access to two things here. So we're going to give it access to our AI model called All-Mini LM L6v2, and also the default SQLite database. So just going to paste this one into the Magic 8 Ball component. I have a bunch of different Spin demo applications deployed. So I have a default database that's hooked up to other things. You guys probably won't run into this. I'm just going to change this. Does this need to be a label, Caleb, in the Spin toml?
To be honest, I don't know.
That's all right. So I need to link this Magic 8 SQLite database to my Magic 8-Ball application. You guys might not have to go through this. I do. Again, if you have any questions on any of this, go ahead and ask Caleb. Cool. So I just had to link that in. SQLite list. Cool. Yeah. So now it shows that my Magic 8-Ball app is linked to the Magic 8 database that I created with the default label. There's a bunch of different reasons why we created labels around the databases so that you can kind of create databases and instead of having to like back them up and delete them, you can just link in a new database and then you still have your other one there in case you wanted to swap out. Okay, so going back to kind of our sample code here, we've got our database set up and hooked up to our Magic 8-Ball app, and we've given it access to the all mini LM model. And here's some sample code that I wrote to be able to kind of take in a piece of text and generate embeddings for each of the paragraphs. So let's see what that looks like. All right, so we're just going to paste this code in here and fix all our imports. So this is a type that I created earlier. In order to kind of store our embeddings. And then one other thing that I was doing here is just kind of generating an ID for it. Not technically necessary, but going to do it anyways. So we can still use quite a few NPM packages. The only thing that definitely doesn't work is things that have native node dependencies. So it has to kind of compile C. Right now, that doesn't work. But we're working on an update for the SDK where you'll be able to bring in some of the kind of native dependencies there as well. Make sure I haven't made too many mistakes yet. Oh, there we go. Didn't include the types. Great, so that should work. And I kind of want like a different endpoint for this, so I think what I'm going to do, what is it, request dot. I'm just going to hack this in here. If I was doing this a different way, I would probably put it into a different spin component, but for now, this will kind of work. So since I want to use kind of a different path to be able to kind of insert these embeddings into the database, I'm going to add a wildcard to this route, and it should still work. I'm just going to kind of intercept that path here. Again, I'm just kind of hacking this in here for the sake of speed. So ready to insert the data into the database. We're going to see here. I'm pretty sure this is going to give me an error, but nope, didn't need to link in the.
just while we're waiting for the app to deploy to the cloud here, any other questions for the group, kind of big stuff about WebAssembly or anything we've done today? Be happy to kind of address that for the group.
So in the context of this kind of embeddings work we're doing here, I'm curious, are there like canonical sources of facts that you know about that would be used for this kind of application?
Yeah, it kind of depends, and this is where like most people kind of start using things like LangChain, where you can say like I want to use this website as a source of information. So a really typical one is like a knowledge base, like an internal knowledge base for your company, where you can kind of go through and index your like internal blog articles or like documents, like Word documents or whatever. And then LangChain will kind of go through there, split out the text similar to like what we're doing here, save it somewhere in like a vector database and be able to look it up that way. Yeah, so there's a lot of like LangChain examples out there around it. I think the creator of Olama was also on our Discord, and he's also adding support for being able to use Olama and Spin, and being able to do kind of retrieval augmented generation using those APIs as well.
Great question.
Cool. Yeah, so this is this is again the 384 dimension vector that gets generated. So here's the text. Weather forecast for today shows 80% of rain. This is the kind of embedding vector that gets saved to our SQLite database. So now that we have a fact in there, let's go through and see if we can use it. So the next thing that we need to do is to create a virtual table inside of our SQLite database. So we've inserted that vector into our table, and now we need to create this virtual table in order to perform the vector similarity search. And this is just, just how this SQLite extension works. So I'm just going to create another SQL file, call it reindex. So every time I would go through and create or add in more context there, I would need to go reindex the database. I'm sure there's a more clever way to do it. This is just the way that I found works. Row. Make sure I didn't fudge the database name. Hmm. Nope. I think it's got to be something with the query. I think the plugins are all enabled by default in cloud. Well, this was working earlier. Let's just point it at. Well, it's fairly anticlimactic that those statements aren't working. I'm obviously doing something wrong. Not sure what it is. Maybe our backing database provider is having an outage. Who knows? Demos, right? So I think that's probably all we have, since can't get this portion of the database query to work. I'll probably post like a fully working example later today to the workshops repo if you guys wanted to check that out. But at least we generated an embedding, so that portion works.
Totally.
You can also do a cosine similarity search in memory if you wanted to kind of query out all of the vectors, load them into memory, and then do the search. Obviously not quite as performant as performing it inside of a vector database, but that is possible too.
We've got about 55 minutes, so we'll be around, happy to answer questions, talk with you guys about spin apps you've been building, do any of that kind of stuff. So thanks for taking the time to attend this workshop.
Yeah.